can actually find structures. Okay, so alright, and then we said that there's some differences between randomized algorithms and what we've been seeing so far. So the first thing is that the algorithms are not always bound to be correct. Okay, so far we always prove that an algorithm returns the right answer. So now all we care about is returning the answer with high probability. Okay, so what happens? Yes.
It's kind of tilted, so this way.
Alright, so now we will only be able to guarantee that the algorithm is correct with good probability. Okay, so that's often what we have. And the same is true with running time. Okay, so we'll be able to say, earlier we could always say that the running time is always smaller than something. Okay, so now we'll say that it's with high probability smaller than something. Do you have a question? Alright, so and very often, as I said, there'll be some trade-off between the running time and the probability. So if you want to be certain, if you want to be really certain, maybe you have to run for a bit longer. Okay, so that's the usual thing. That's one of the trade-offs. Okay, and we saw a very toy problem where we said that if you're given an array and you're told that at least half the entries are 0, you have to find one position in which a of I is 0. So last time I said, okay, so this is one of the canonical examples of a randomized algorithm, because now you can say, okay, I pick a random index and see if it's 0 or not. Okay, and that's going to succeed with probability half. And if you try this a bunch of times, the probability that you fail is negligible. Okay. And this is what I said. Then we said that this is not so much of a toy problem. A lot of interesting problems can actually be reduced to something like this. Okay, so we said that, or rather not quite reduced, but it's in the sense of, at its core, this is what's going on in those problems. Okay, so one is, I said, primality testing. So you're given a number n, and you want to tell if it's prime or not, and your running time should be logarithmic in the number of digits. Or rather, it should be polynomial in the number of digits. So here the goal is poly in number of digits. And that's equal to saying it's poly in log n. Okay, so this is a primality testing problem, and essentially the idea behind the test is that there is something called a Fermat test that you can do for some number x between 0 and n. And what you can show is that this, if n is actually composite, then this test actually fails for more than half the integers less than n. And I didn't tell you what this test is. It's a number theoretic test, and this is nice because this is kind of like the previous problem now. Because for each x, the test can be done in time polylog n. Okay, and so for this reason, I mean, you essentially reduce to that kind of simple case. Because if the test fails, then it's like finding a 0. So that's why I had this toy problem. And we also talked about what's called polynomial identity testing. So I give you two multivariable polynomials, but without actually giving you the explicit representation. Okay, so I said that you can sometimes define polynomials as determinants of matrices and stuff like this. And but the key idea is that if you want to test if two polynomials are not equal, then you can just test at a random point in the domain. And there is something called the Schwartz-Zipfel lemma, which basically says that if polynomials are indeed unequal, then they differ in a lot of places. So that's again like finding a 0 in that example. So these are all just examples. So where this randomization very easily helps. In your homework, you'll see another example where randomization helps in a very nice way. Okay, so in a communication complexity setting. So you will see that. Okay, so what we started out trying to do now is, so these are examples of randomized algorithms. So these are kind of very simple examples, right? We're not doing anything clever with randomization. Essentially, we are observing some structural properties of the problem, and we're saying, oh, now if I had randomization, I can easily exploit that structure. Okay. Now let's try to do something where, in some sense, the algorithm itself is randomized and it's a nice iterative kind of algorithm. Okay, so the example we'll look at is median finding. We've seen this in some of the early lectures in the course. Okay. And it was a classic example of divide and conquer, if you guys remember. Okay, so what is the problem? You're given an unsorted array and some integer k. Okay. You want to find the kth smallest element. I'm calling it the median problem because if k is n by 2, it's the median. Okay. So, and you want to find the kth smallest element. So, do you guys remember how we did this? So, the answer is here because I don't have animation, but yes. So if you remember, we tried to divide and conquer, right? So that's basically what we're doing. We tried to find some element that was nearly in the middle of the array, and because of this, we could divide the problem into two subproblems. And I said that the classic deterministic way to find an element that's almost in the middle is this tricky thing of pairing into groups of 5 and finding the median of medians. Okay, so what randomness allows you is something much simpler. That's what we're going to see today. Okay. So, right. So the idea was you had this array, and if you could find an element that's kind of in the middle, okay, middle in the sorted order. Okay, so almost middle means in the sorted. Then you can, essentially what you can do is you can process the array into things that are less than this, things that are bigger than this, and then you can recurse into one of the portions. So that was the idea there. So that was median finding. And now, so when we want to do, if your goal is to now come up with a randomized algorithm, a trivial way is, what if I pick this pivot element or this my guess for the almost middle element as just a random element. Okay. And that's the main idea. Okay, so if you had, so this is the array A. If I pick a random element, okay, so what is the probability that in the sorted order, this is going to be in one of the extremes? Okay, so this is A, and let's call B the sorted order. Sorted form of A. Okay, so both A and B contain the same elements, just permuted. So if I picked a random element out here, what's the likelihood that it's going to be in, let's say, the last, let's say, n by 10 and the first n by 10? Is it likely that it's going to be in one of these regions?
1 by 5.
Yeah, it's pretty unlikely, right? So it's going to be, it's going to be about 1/5. Right? So with pretty 0.8, 80% of the time you're going to be in this zone. And this way we are using randomness in some sense, right? Because we picked the random element of the original array, and that's equivalent to picking a random element in the B. Okay, and that's the nice thing about randomness. Even though you don't know the sorted list, you can think of just picking a random element here. So that's the idea. Okay, so that you are pretty likely to cut it in almost half. Okay, not almost half, but like reduce the size significantly. So that's what we call the random pivot. Okay, so let me write down the algorithm. Okay, so the algorithm is pick random element of A, partition A into A. Okay, let's call this A of I. Okay, so into A plus and A minus, where this is less than or equal to A of I and bigger than A. So let's assume all the elements of A are distinct for simplicity. Okay, so that's what we're assuming, and this is how we do it. So is the definition of A plus and A minus clear? A plus is things that are bigger than or equal to, sorry, less than or equal to A, and A minus. And now, right, so now we have a nice picture. Now we have divided A into two parts. So you have the A plus portion, and then you have A of I. Okay, A of I is actually, the way I defined it, it's in A plus. And then you have the A minus. Okay. So now, how do I find, suppose I give you some K and I ask you to find the kth smallest element of A. How would I go about doing it? Let's just recap from before. So remember, A plus and A minus are not in sorted order, right? You just went through A, put everybody, in order, put everyone who was less than A of I in A plus, and put everyone who is bigger than A of I in A minus. So these are again unsorted things. Now, if I want to find the kth smallest element in A, how would I do it? Yeah.
So I would be sure that the pivot is in its sorted index.
Yes.
So I will see that at what index it is.
Okay.
And if it is greater than the current index, I know that my solution lies in the left index.
What is current index?
The index is the pivot.
So what you're saying is, don't think of an index, right? You have these sets A plus and A minus. Okay. So, and I want you to find the kth smallest element of A. Okay. So, you're right in the sense that this portion of the array, what you know is that all elements are less than or equal to A of I. A of I don't care what I is, right? So it's just some random index. Okay, so but I know that it's some real number, and the elements in A plus are all less than or equal to that real number. And same with A minus, they are all bigger than or equal to this real number here. Now I want you to find the kth smallest element, and if I told you that, in some sense, so here there are, let's say, 100 elements, and here there are, let's say, 50 elements. Suppose I told you K was 25. Do you now know which set to look into? The left one, right? Because I know that there are 100 elements less than or equal to this A of I. And so there's no way it could be on the right side, right? So the 25th smallest element, there's no way it could be on the right side. Okay, so this is how we did this. Okay, and this is how it recurs. And the problem is that if your A of I was somehow in these corners, then one of these sets will be significantly bigger than the other. And now we kind of argued that you're unlikely to be in the corner, right? So at least in the first step, with decent probability, it will be a reasonable split. Okay, so this is what. Oh, okay. Let me finish that one so that we don't get carried away. Okay, so partition A into A plus A minus, and then depending on K and size of A plus, okay, recurs into either A plus or A. Yeah, I won't write the details because we've already seen this. So this is the algorithm, right? And at least from previous slide, so in the first step, this is a recursive algorithm, right? Because you recurse into the subarray. At least in the first step, we are pretty sure that the problem size reduces by a reasonable amount. with at least 4/5 probability, your problem size is decent. Yeah.
What kind of probability will you define as small enough?
Yeah. So I will write it. So at the first step, right? So with probability at least 4/5, the split, the size of the problem reduces by a factor of 9/10. Okay, so this is what we saw in the previous slide, right? So this argument of saying that the probability that that your pivot comes from one of these two extremes is at most 20%. Like saying with probability at least 80%, you have, the problem reduces by at least a factor of 9/10. Okay, because if you are out here, the worst case is that you search in this subarray or one of the two extreme subarrays, and then your problem size is less than 9/10. So is that point clear? Maybe I will pause so that if you have a question. Does everyone see that the problem size reduces by a factor at least, by 9/10? Yeah, some of you don't appear convinced, so I'll ask you a question. Yeah.
Shouldn't it reduce by 1/10?
So it depends on what you mean by reduce. Yeah, so what I mean is that the new problem size will be less than or equal to 9n by 10. Okay, so new problem size 9n by 10. Okay, so yeah. So this is fine. What we are saying is that with decent probability, your problem size reduces in the first step. But the first step is not what we care about. We care about something recursive holding, right? You might say, oh, okay, I'll have some probability for the first step. I will multiply these probabilities, okay, and that's at least the success probability I'll have at the very end. You'll soon realize that if you do this, you run into trouble, because your probability of succeeding is not quite very high. It's just 4/5. And if I multiply 4/5 a bunch of times, this is going to reduce to a very small quantity. So this is not the right way of doing this, right? So we need some cleverer way of doing this. And the way we are going to talk about this is to talk about the expected running time. Okay. So I guess this is 2 steps ahead, but so we are going to talk about the expected running time of the algorithm. Okay, so let's. So again, is the notion of expectation, is everyone comfortable with this? We saw this last time also, right? So running time for these kind of algorithms depends on how the random choice performs. So the running time is a random variable, and for a random variable, any real valued random variable, you can define the expectation, and that's the quantity we're interested in. And the idea will be, and this will be a common idea in many randomized algorithms, to somehow write a recurrence for this expected running time. And the recurrence will look very much like recurrences we've seen. It's just that the quantity that we are defining will be the expected running time. Okay, so let's define, I won't call it T of n because that's what we've been calling it before, but let's call it S of n. Okay, this is the expected running time of the algorithm on an array of size n. Okay, so this is a randomized algorithm, and depending on where you where you pick the pivot, the running time changes, right? So you get a problem, subproblem of a different size. Okay. And we want to write the expected running time, and we want to write some kind of a recurrence for the expected running time, S of n. So how would you go about doing this? So we want to, as always, right, as you write down the running time, you can also stare at the algorithm, try to write down a recurrence for this. So what would be a recurrence for this, looking at the algorithm itself? Yeah.
So at the n+1th step, I could have a array whose size can range from 1 to the size of the tn plus nth step. So I could take the expected.
What is the n+1th step? What do you mean by that?
So sorry, not t's. So
Yeah. So is the question clear? I want you guys to look at the algorithm and see if you can come up with a recurrence for this S of n. Right? So can I write S, and by recurrence we always mean write S of n in terms of things that are smaller. So yeah, so how would you go about doing this? Like suppose I made it easy for you, right? Suppose I told you that I picked the rth smallest element in the first step. Now what can you say about the expected running time? Okay, so suppose this is like side calculation that we're doing. So suppose pivot was the rth smallest element. Now we know that if k is less than r, then you would go into the smaller thing, otherwise you would go into the bigger thing. Okay? So depending on what r is, it could be one thing or the other.
Excuse me,
Yeah.
when you say the R, the smallest element, it is in array A or array B? The sorted one or the unsorted?
What do you mean? You tell me. So both the arrays have the same elements, right? So if the so both are the same.
Pick the R smaller elements and its position in the unsorted array may be different.
Yes, but when I say the rth smallest element in this array, it's the same whether this array is sorted or not, right?
Okay.
Right. So that's the definition of the rth smallest. Like if I have an array and I say pick this, give me the smallest element in this array. Right. So it's the same whether you have it sorted or not. I hope it's clear. Yeah. Okay. Yeah.
So Sn equal to n minus r by n into S
Wait. Yeah. So it's what? Sn is like suddenly is giving out a formula. So yeah. So in the rth case, you're saying Sn equals
n minus r by n into S times Sn minus r
okay.
plus r by n times Sr.
Where do you get the r by n and n minus r by n?
So I get two splits based on the pivot.
No, so I'm not asking you to say what's the probability that the pivot was at the rth position, right? So far I'm just asking you, what is the probability? Suppose the pivot was the rth smallest.
Okay, so it will just 1 by 8 instead of r by 8. Because at the first trial I may get the small element that I am done, and then I am left with the rest of the array and I reverse through.
So I think both of you are kind of right, but I think that's not the question I'm asking. Okay, so I'm not asking you to analyze S of n directly, right? So what I'm saying is, suppose my pivot was the rth smallest element. Now it's a deterministic process, right? So at this point, at least the first step was deterministic. I already fixed which element you picked. If k was smaller than r, then I know that I'm going to get S of r. Okay. So at this point, the running time is basically if k is less than r, less than or equal to r, then it's s of r. If k is bigger than r, it's s of n minus r.
Plus 1.
Yes, plus n. Thanks. Yeah.
Otherwise, it's recursive.
Yeah, plus n.
Work it off.
Okay, so the plus n is because you've got to form these a plus and a minus, right? So you have to go through the original array A and put things into different buckets. So you have to go through the full array once. Okay, so it's this. Okay. But yeah, so I'm going to be kind of lazy about it because I don't know what k is. So k could be whatever. So I'm going to say that this is always less than or equal to max of SR and Sn minus r and plus n. So I'm going to be lazy about this. But this I know for a fact. And yeah, so this we know. So now we could write a recurrence for S of n, right? So in the sense that, what is the likelihood that I picked the rth smallest element now? For any given r?
R by n. 1 by n.
1 over n, because you pick a random element, it's equally likely to be the rth smallest element for any r, right? So it's so that's the idea. Okay, so you can say that overall S of n is now, I'm going to just write a smaller than or equal to here, and it's less than or equal to. Now it's a sum over all the possible r's of probability that, so let me just write it down, probability that you choose rth smallest times the time given its rth smallest. Okay, times the time for the r. Okay, and this is the time of r. That's what I mean by that. This is exactly what the algorithm should be. I mean, this is the definition of the expectation, right? It's I mean, at this point it's equal to this. Okay, so the definition of the expectation is sum over all possible r, probability that you chose that r times the time given that you chose that r. And this one we have bounded this by this is less than or equal to. The probability is always 1 by n, so it's 1 by n times sum over r of max of plus. Okay, so we need to have a new slide. Because it's messy, I'm going to write it down again. So I have S of n less than or equal to 1 by n times sum over r equals 1 through n minus 1. Actually, maybe I should try that, because I can also pick the nth largest. The max of SR, S n minus r. Yes. Yeah.
Inside the max block,
Yeah.
should it be the expected time or should it be the actual time? Does it matter?
Yeah. So what should it be? Should it be?
Should it be the actual time, right? That's how we defined it. I mean, we took the max of the actual time and then we multiplied by the.
Well, see, the algorithm even recursively is a randomized algorithm.
Yeah.
So even in the next step, you're going to do something probabilistic. Okay. So when you're computing the expectation, so even the next step is randomized. Therefore, you can only talk about it. So yeah, but that's a good point. Okay, so this is again the expected runtime. The reason is that recursive algorithm is also randomized. Okay, so that's what this is. And now, okay, so let's. This looks strange, right? So it's it's like a max of a bunch of things. So firstly, you could say, okay, I'm going to simplify this a little bit. Okay, so we'll. So the n can be got out because n is common to everybody. So you can say it's n plus 1 by n sum over r equals 1 to n. Okay, so this is the same thing. Now you could say that, one way, there's many ways to solve this kind of a recurrence, but what you should note is that this is just simply a recurrence in terms of the s's. Right, so I'm just saying, if I gave you s of r for everything up to n, you should be able to write down what s of n is. Okay, so yeah, so I'll wait here for a bit for you guys to realize that now I've essentially reduced this problem to algebra. Right? There's nothing probabilistic anymore. Okay, and the point is that, and because I've written an expression for the expected time, and this is what that is. So make sure you realize what we have done in this step. That essentially now for the expected time, we have come up with just a general recurrence, which we can now use all our techniques that we know to just solve. So that's what we have done here. So make sure you understand this point. All right. So good. So this is what we've done. And now, so remember our goal is to prove some kind of, so what would you hope is the solution to this recurrence? Would you expect s of n to be something like n log n, or
Better than n log n.
yes? So you want it to be better, yeah, of course. Even sorting would do n log n, so hopefully it would be better than n log n. Best you would think of is n, because there is a plus n here, so I don't think you can do better than n. Okay. So you might say, okay, I'm going to guess that s of n. So that's what we're going to do, right? So less than or equal to c times n for some constant. Okay. And now plug it into the recurrence and hope for the best. Right? So this is what we always do with recurrences. We try to guess the answer and hope for the best. Right? Hope that inductively you can prove it. Okay. So let's try doing that. Okay. So any questions on this?
Can we just enumerate the r from 1 to then I2 so we can remove the max?
Yeah, we're going to get to that. Yes, we will. Yeah. So I think what she's observing is that s of n better be a growing function of n. Therefore, if I know, I could go from r going from 1 through n over 2 and have a factor of 2 out from that. Okay, so that will come out from the calculation anyway. So let's try to show this. Okay, so our guess is this, and as usual, yeah. So now we can just plug it in, and we get something like. So the right side of this. Okay, so again, proof by induction. right? And we say that, assume this is true for integers up to n. Okay, and we want to prove it for n, right? It's the usual thing. And then we say that s of n is less than or equal to 1 by, there's an n plus 1 over n times sum over r equals 1 to n. Now this is a pretty clean expression, right? This is just max of CR and C times n minus r. Got to be a little bit careful with the summation of r being equal to n. So, yeah, so there's a bunch of ways to get around this, but let's, nothing will hurt in this process. You could get the C of n out and, sorry, this should be S. Right, you could, in the last step, you could get the S of n minus out, get it to this step, and nothing much will change. Okay. But for now, let's just assume that this summation is only until n minus 1. So, yeah. So this is one small step that I'm skipping. Okay. So otherwise, you'll just have the 1 minus 1 over n out here. Okay, which is very simple. Okay, so, alright. So this is what we have, right? So you have C of n. C times n is what you guess is the bound on S of n. And this is what you have on the left, on the right. And now, this is again easy to so now we have an expression which basically says S of n is less than or equal to n plus 1 by n. And now we're going to do the trick that she was saying. So it's, I'm going to write down the sum as, for r equals 1, we're going to just get C times n minus 1, right? Because that's the max. R equals 2, we're going to get C times n minus 2 and so on. So we're going to get actually let me get the C also out here. Okay, so we're getting a C here, and if you think about it, you'll get 2 times n minus 1 plus 2 times n minus 2 so on plus 2 times n over 2. Okay. And this is based on the observation that she was making that everything, between n by 2 and n, the max of the 2 will be the same. So that's why you get a factor 2 and you get something. Now, this we know how to evaluate, hopefully. So all of us, so we can write n plus 2c by n. And this is sum of integers up to n is n squared by 2. Right? N times n plus 1 by 2. Right? So it's, let me write as roughly n squared by 2 minus n by 2 whole squared by 2. So that's what that sum is. If you guys want, you can be very careful. You can add n times n minus 1 by 2 minus n by 2 times n minus 1 by 2. Okay, but it will come out to the same thing because that n will just make that extra term a constant. So you get something like this. Now this would be equal to n plus 2c by n times 3. So okay, last time I worked this out, this came out to 3n squared by 8. Okay, so and let's check. So you get this, and this is n times 3c by 4 plus 1. Okay. So this is just algebra, so you guys don't need to follow it, just take my word for it. Okay, so this is what you get. Now, so this is what we get assuming the inductive hypothesis. Right, so if you assume inductively that S of n is less than C times n for integers less than n, This is what we got. Okay. And now, for the inductive thing to hold, we want to show that this thing is less than or equal to Cn. Right? And then we would be done. Okay, so to show the inductive step, we need n times 3c by 4 plus 1 less than or equal to Cn. And this is true as long as C is bigger than or equal to 4. Okay. So you could have done the whole induction with C being equal to 4 and everything will work out. Okay, so that's all the same. If you want to be safe, you can put 5 and everything will work out with some slack. Okay. Yeah.
How can we get 2 plus n minus 1 and the first?
Oh, the first line? Yeah, so it's basically using this fact. So what is this if you write it out, right? So it's the C came out. C is just something that comes out. And then it's max of R and n minus R. When R is 1, this quantity is n minus 1. When R is 2, it's n minus 2 and so on. When R is n by 2, this is n by 2. When R is n by 2 plus 1, okay, this will be again n by 2 plus 1, because this time now the R term starts to dominate. Okay, so this is exactly what she was saying, right? So that the function max of R and n minus R, so it basically looks like it will drop from n to n by 2 and then increase again. So everything will appear twice basically. Okay. So that's why, yeah. That's why I have a 2. Okay, so what have we shown here, right? So we've shown that the expected running time is less than or equal to 4 times n. So this is a pretty nice fact, in the sense that the best deterministic algorithm we know was also a constant times n, but that constant was actually much bigger than 4, right? It was like 20 n. And this is randomized algorithm. Constant looks much better. It's like something like 4 n. So that's good. So now it's the question is, this is just the expected running time, right? How close? So suppose I have an instance and I just run this algorithm. Will I be close to the expectation or will I be far from the expectation? Okay, so do you guys understand what I mean? So if you have a random variable, right? So if I had an arbitrary random variable, something that looked like this, this is some random variable x. There is some this has some distribution like this. The expectation could be something that's out here. But you could be unlucky and you could have a runtime that's significantly higher. That's like way out in the corner. Now, the natural question you might want to ask is, what's the likelihood that you're actually very far out? Okay, can you bound the probability that you're actually very far out? Okay, so that's the next question that we want to ask. Okay, so we know that. Okay, so the question is, we know that expected value of runtime. Let me just call it t for now. T of n is less than or equal to 4n. Now, what is the probability that it's more than 20n? Can we bound things like this? Okay, so that's the next point. That's the next point we're going to try to study. But is the motivation for this clear? So yeah, so if it's not clear, you will see some of these things in the homework. But you'll see some basic examples of this in the homework. But we're going to see something stronger now. Okay. So yeah, so very often this is something we care about with with algorithms, because maybe the running time looks like this, right? So it's very far out and something like this. Okay, so this is, suppose this is the probability distribution for the running time. Then actually maybe this peak could be much higher. Okay. So if this is the probability distribution, then the expectation will be something like this. There's still a reasonable probability that you lie out here. Okay, and this is a bad situation for our algorithm, right? Because then with decent probability, it's actually pretty far out. You don't want algorithms of this kind. You want algorithms which are, where the tail actually drops off, and most of the time you're actually very close to the expectation. So that's what we're going to try to bound. And what we'll see today is like a very first cut bound for stuff like this. And so we're going to concretely start with this question. Okay. So what is the probability or rather can we bound the probability that T of n is bigger than 20n? So 20 is constant, some general constant I chose which is bigger than 4. Okay, so the expectation is 4n. Now suppose I tell you what's the likelihood that it's bigger than 20n. So how can you bound something like this? Right, so that's what we're going to ask today. And so the first question I'm going to put to you is, could it be that this probability so let's call this event E, right? Actually E is bad notation. Let's call this event F. Okay, so could it be that this probability is equal to half? Right? What do you guys think? Why not?
Because first we're assuming that the random choice may not lie in the edge case like n by 10 and n by 10.
Okay.
So we are lying 80% in the mid-range case. So it's highly unlikely that we'll be in the edge and we want to find this the smallest element. So I think it should be
Sure, but what makes you say that? I mean, the recursive steps won't take 20n. I'm not telling you the first step takes time 20n, right?
It may take, but it's highly unlikely.
Yes. How do you bound that? How do you say it's highly unlikely?
Because it's highly unlikely that I will pick the edge cases every time in every recursive stage.
Right. So the intuition is correct, but why do you have to do it in every step? It could be that you maybe pick the edge cases like 3 or 4 times, and problem size doesn't reduce by enough, and then you run into issues. Right? So yeah, so that's good line of thought, but it's tricky to make it formal. Okay. So what I'm actually going to say today is that there's like a very, very easy way to argue about these things. I mean, if you want a weakish bound, if you want a good bound, what you're saying is what one has to do. Okay? But if one wants a somewhat weak bound, like suppose I want to say that you can't have a 50% probability that the time is more than 20n, then there's actually a pretty trivial argument. That's what we're going to see today. Okay? So somebody else? Yeah.
So it can't be too high because the expectation value has to be 4n.
Right, so this is what we want to capture. Okay, so what does it mean that the expected value is 4n? Right, so if the expectation is 4n, so you have 4n out here. This is what the expectation should be. And suppose I have, and here is the 20n. So you are saying mass, the probability mass in this region can't be half. Right, can't be more than half. And why is that?
because then something else would have to balance. I mean, the lowest possible value is 0 here. So even if you had the rest of the weight at 0.
Yeah, so that's the key thing, right? So what he's saying is the running time is always positive. Okay, it can never be negative. So if the you should always think of expectation as some kind of a center of mass, right? So you have the probability mass of this random variable. Okay, so okay, so I have a distribution that looks like this. It starts off at 0, and I don't know how it exactly looks like, but maybe it looks like this, right? So, and this is 20n. We want to say that the total mass on this side is less than half. And I know that the expectation is 4n. And by the definition of expectation, it's some kind of a center of mass, right? So the expectation of a random variable t is let's say the integral over small t, probability that capital T equals small t times small t. Okay, so and this is what he was saying intuitively, right? And basically the small t here, I'm choosing it to be things that are bigger than 20n. And if the probabilities out there add up to more than half, then something on this side needs to balance that, and you have to, so here I'm assuming this probability is half. And there's not enough, and if I want the average to work out to be this number, alright, so if I have half the mass over there, I have only half the mass left over to play with, right? And I could place it somewhere in this range, but the distance between here to here is something like 16n, right? And if I need to balance that out, I've got to have 4 times the mass on this side. And that's roughly the idea. Okay, and everything is less than or equal to, is bigger than or equal to 0, so you can't have so much of the mass. And yeah, we'll make this formal in a bit, but this is the intuition, okay, that you can't have too much mass that's too far away, because then the expectation will be way too high. Okay, so that's so form. So let me now make this argument formal. Okay, so it's actually very simple to make it formal. So we all know this is the definition of the expectation. And suppose I let, okay, actually I'll first simplify this. You can always say that this is bigger than or equal to integral from 20n to infinity. Okay, this is t going from 0 to infinity. So t going in, probably going from this to this, of 20n times probability that t equals t. So, do you guys agree with this? Because there's a little t. Firstly I'm saying that I have an integral from 0 to infinity. I'll say it's bigger than or equal to the integral from 20n to infinity. And whenever t is bigger than 20n, t is bigger than or equal to 20n. So I could write 20n out here. Okay. And then I have that. So maybe I should write the intermediate step that I skipped. This is bigger than or equal to integral from 20n to infinity, of t times probability of capital T. This t is always bigger than or equal to 20n in that interval. So that's why I have this. And yeah, now I have this. This is like 20n times integral from 20n to infinity capital T equals T, and this is exactly 20n times probability that capital T is bigger than or equal to 20n. That's the definition, right? Of probability that you're bigger than or equal to 20n is exactly integral from 20n to infinity of probability. So, and this is what this is, right? So I know that, and this implies that probability that T bigger than or equal to 20n is less than or equal to expectation of T divided by 20. Okay? So this is just basic algebra that I'm doing. Okay, so I'm not doing anything fancy here. I'm just using the definitions of the probability, of the expectation. The definition of the expectation is that, the first expression, saying that that is bigger than integral from 0 to infinity is bigger than or equal to integral from 20n to infinity, because all terms are not negative. And there I'm bounding that T by this. I'm doing some basic manipulation. So I'll pause here for a bit, and then I'm just rearranging the terms. So I'm dividing through by 20n to get this. Yeah, I'll pause here because maybe some of you are seeing this calculation for the first time, so you should try to absorb it. Questions? And actually, this gives me something stronger than what he just said, right? I mean, than half, right? That I know that E of t is 4n, so this is actually 1/5. Okay, so this calculation actually tells me that probability that you are more than 20n is actually at most 1/5. It's like 20%. 20% isn't great, but it's a start, right? It's telling you that at least 80% of the time your run time is going to be less than 20n. And this is, so if you all agree with this calculation, then I'm going to move to a generalization. Battery is running low, so hopefully it will last the next 10 minutes. Okay, so alright. Okay, so this is actually a very common thing, and this is what is called Markov's inequality. Okay, so it's a very simple fact, and what it says is that if you have any non-negative random variable, it's important that this is non-negative. And this again, the intuition is what he said, right? So if you allow negative entries, you can have like a small probability mass very far negative. That's going to balance out things, okay? Because at the end of the day, the expectation is the average, right? So that's going to balance out things. So if you have any non-negative random variable, and if you have an expectation of C, then the probability that the variable is more than t times the expectation is at most 1/t. Okay, so my computer died, so I think it's an emphatic place to die. But, so this is, so turns out I lost the dongle that connects directly to the iPad, so that has been the problem. So let me do one thing. So we don't have too much left, so I'm going to use the board for now. In the Sorry? Oh, you have a Lenovo chart?
Yeah.
Oh,
This is the same time.
you're a savior. Yeah, let's hope that. No, actually, this
Oh, the USB.
yeah, it looks like a USB. It's not quite.
哦，那种。
Yeah, anybody else with a Lenovo chart? Okay. Yeah, otherwise somebody left to run too. Oh, yeah, I thought it looked small like that. Let's see if this works. Yeah, so I think the battery runs out way faster if you're projecting, which makes sense, but I didn't realize this. So good, this was fast. Thanks for. Oh yeah, thanks for. I somehow thought you were one rope here. Yeah. So this is great. So now, so this is what is called Markov's inequality. Okay, so if you have any random variable that has expectation c, the probability that it is t times that expectation. If t is any number. You could, I mean, so in our previous example, C was 4n and T was 5. Okay. So we said that probability that, oh sorry for the T's, but this capital T, which is the running time, which is like x here, it's a random variable, is more than 20n, is less than or equal to the expectation divided by 20n, which is something like 150. Okay. So that's exactly Markov's inequality. So it's basically says that, and this is the most widely applicable inequality. Okay, so in some sense, you could think of most other inequalities being reduced from this. It's yeah, and it basically says any non-negative random variable have an expectation. You're not that far from the expectation. So this is okay, but it's not very satisfactory in the sense that there's still a 20% chance of failure, right? So, I mean, yeah, so in our example, you can actually show much stronger concentration bounds. I mean, I think you can even show that the probability that the running time is more than 20n is actually significantly smaller, something like 1 by 2 to the 10 or something like this. But yeah, this will be trickier to show and it involves a lot more computation. So yeah, we won't get into this, but very often you can show much stronger bounds than what Markov's inequality gives you. But Markov's inequality is like a first cut. It always gives you some bound, right? So it tells you that you won't be too far from the expectation. Okay. So that's usually the thing. And there's two ways people usually go about things. Okay, so sometimes, like in this case actually, you will find it hard to come up with an argument that says something like this. Okay? But there's a standard way to recover from these things, which you should kind of remember in randomized algorithms, which is, so does anyone know? So suppose I told you, here's an algorithm with probability at least, something pretty weak, right? With probability at least 60%, it has runtime less than or equal to, let's say, 10n in this case. Okay? So, suppose now I want a higher probability of success, right? Suppose I want probability of success being, let's say 99%. What can you do? I mean, is there something you can do in a black box way? Yeah, so that's what you could do. I mean, you could increase in time, but I just said the analysis is messy, right? At least, maybe it's not too messy, but I don't know of a very clean way of analyzing this particular thing and getting like 99% right bounds without actually doing a lot of calculation. Okay? So, but if you had to do something like this, then what you could do is just run it multiple times. So you say, okay, I'm going to start running this algorithm, cut it off at time 10n. Okay. And I know that 60% of the time this would have actually worked. Okay. If it worked, it's great. Otherwise, I just rerun it, cut it off at time 10n, okay, and keep doing this. So suppose I now do it 5 times. Okay. So I ran this algorithm 5 times, cutting it off at 10n. Okay. What's the amount of time I have spent? It's at most 50n, right? Because if I have failed all the time, then I would have spent 50n. Otherwise, I would have found the solution, in which case I'm happy. So what's the likelihood that you have always failed? Yeah, so it's something like 40% raised to the power of 5, right? So that's like 2/5 to the power of 5. And this number you'll see is a pretty tiny number. So I don't know what the answer is to this, but it's probably tiny. So it's less than half to the 5, which is like 1/32, right? So this is, and as you can see, if I now raise it, if I do it 7 times, I'm going to get 99%. Okay, for sure. So this is a standard way of, so it's called amplification, and it basically it's a way of boosting the probability of success. Okay. So very often, even though Markov's inequality is kind of weak, we are happy with it because we say that, oh, okay, you know what, I repeat it enough times, I'm going to get good success. Okay. So that's one way to view these things. I mean, there are some situations in which you can't repeat, for which you will need better inequalities. Okay, but we will get to some of those things. Okay. But is this point clear? So this is repetition. Boost success probability. Alright. And this works for problems where you just have to succeed once. And you could ask if there is a better bound in this case, and we'll see examples of this, but this is a whole area by itself. It's this space called concentration inequalities. Okay, and the general theme of this area is you have some random variable, you want to show that it's tightly concentrated around its expectation. Okay, so it's so the probability distribution kind of looks like this, where it's suppose this is the expectation. This is the random variable x, this is the probability. Right, so if the distribution looks like this, expectation need not be at the peak, but whatever, right? So this is the expected value. So we want to say that probability that it's far from the expectation is small. Okay? So you want to show that this height is tiny. And these kind of inequalities are called concentration inequalities, okay, where you show that your random variable is very close to its expectation. And how close you get depends on the random variable, and usually, it's usually a function of the standard deviation and so on. So we'll see examples of this, and we might even see a more general thing. Okay, so the simplest setting in which we'll see examples is this next problem that we're going to study. But before we move on, is the median example clear? So we saw very simple random pivot algorithm, and we showed that the expected running time is something like 4n. Now you can repeat it, and using Markov you get a pretty good bound. Okay. So that's what we have. Right? Okay, so the next example of randomized algorithms, this is again something all of you would have seen. So we'll see how you actually analyze these things. So sampling to find averages. Okay, so this is something we do all the time in real life, right? So you have a whole bunch of numbers. You want to find the average. One way to do it is to go through all of them and find the average. If the set you have is too big, you just sample. Right? So this is what we do to find like election results and stuff like that. Not the final result, but to estimate it. Okay, so this is what we do. And the problem to state is very simple. So you have a vector of integers. Let's call this a1, a2, up to an. And the goal is to find / approximate 1 by n sum over I. Okay. So sometimes you know capital N, sometimes you don't even know that. So right. So now, So what? How do we solve it by sampling? It's the obvious thing, right? So you pick a bunch of random indices. Pick indices uniformly at random. It's important that they are uniformly at random. IK. And I'm going to add a word which some of you may not have seen, and compute the empirical average. Okay, which is 1 by k sum over I a of ik. Sum over j a of ij. Okay, so I'm going to pick a bunch of indices and I'm going to do the empirical average of those. The way I'm writing it as a, so I have this word with replacement. Do you guys know what I mean? Yeah, so what with replacement means is that it's not like I'm enforcing these i's to be distinct. So I'm just saying, think of it as a multiple rounds of this one-shot sampling where I say, oh, give me a random AI. Doing that multiple times. So it could happen by chance that I get two AIs that are the same. I mean, even after like the second step, maybe I was unlucky and I got the same AI twice. So that could happen. But yeah, so that's what we want to say by, that's what I mean by with replacement. And this is the way you compute the average. Now, how good is the estimate that you get? So So do you see issues for certain types of A's? I mean, would this work for any A and give you a decent estimate for the average? Yeah, so what he's saying is that if A is not uniform in some sense, so, and what do you mean by that?
I mean, if it's not normal, there are some areas like clump together.
Well,
Like the variance.
clumped together is fine, but right. So what we don't want is, suppose I had an array that looked like this, right? So if I had a whole bunch of zeros and I had one entry that was 100, okay, so 1000. Okay, so and I had 1000 entries like this. Okay, so 1000 entries. So the average of this is 1 because the sum of all the things divided by the number of elements is 1. Okay. But if I sample, I'm pretty likely to get 0, right? Because unless I sample a lot of things. Okay. So this is usually a problem, okay? And it's roughly what you're saying, that large elements cause problems for sampling. Okay, so that's the usual kind of a thing. So having some entries much larger than the others. Cause problems. Okay, so that's the problem. And yeah, I mean, as you can see, there's not much we can do about this, right? I mean, in the sense that if all you have access to is getting uniform samples, then this is basically all we can do. Okay, so you could say maybe I can sample in a cleverer way and so on, but without knowing the positions, there's no way you can do it. Right? So what we're going to do is do the next best thing, which is, okay, suppose I tell you that I have integers in a certain range. Okay, so if the magnitudes are not too high, then can you get a sample? Okay, and how good is the estimate? So I think we are running kind of out of time, so maybe we will skip this for next class. Okay, so but this is the next thing we're going to see. Okay, that suppose I have things in a range, then can I get a decent estimate? By the way, those of you who haven't given projects,